Hey everyone, this is the group project for Grayson, Kevin, and Rigo for CS454. Our final project was to go over a problem given to us in Project 1 and see what we can do to optimize it. So the problem that we were trying to optimize was given an integer x and an alphabet of single digits, find a number comprised of strictly just the alphabet that's divisible by x. So for this example, the one we went over in class was given the number 7, we want to find a number that's made up of just 3's and 8's. And when you divide it by 7, it divides evenly. So to do this, we drop a DFA, and the states are going to be the remainders for our numbers. So because we have the number 7, we're going to have a remainder of 0 through 6. And if you look at our states, we have numbers 0 through 6, or 7 states. And then our alphabet allows us to have arrows between the different states, showing us how the DFA would work and how we would rotate and move along. And once we hit 0, we have found a number that is divisible by 7 and is comprised of strictly the numbers that were given in the alphabet. Now, it's important to note that the x is going to change the number of states you have. So if you have a couple thousand, you're going to have a couple thousand states. And if you have more numbers in the alphabet, you're going to have more transitions between each state. And you can easily have 3, 4, or 5. You can have technically all 10, but that wouldn't really be a really good problem to try and solve because any number would be accepted. But if you have 5 or 6 transitions, you can see how this blows up really quickly, especially with a big number. So our problem was to try and optimize this and see what we can do to do bigger numbers and make it a little bit faster. And just a quick reminder that these states and transitions are all represented by 3 tables that we did in class. It was a visited table, a parent table, and a symbol table. So we're going to go over the programming aspect of what we did and how we optimized this and show you what optimizations we're able to create. So let's go ahead and start presenting the base case before we start talking about optimizations. Our base case is going to be a serial version of Python, and the base case inputs are going to be an alphabet of 3, 4, 5, and 6. A base case integer value for x is going to be 707, 415, 53. And our answer is going to comprise of all numbers from the alphabet, which is what we expect. And now we're going to shift our focuses on times. In the Python implementation, we ended up taking 204 seconds. After a few meetings with the teacher, we ended up going down a path of trying to get Java to work. Now our Java implementation is also in serial and ended up having a speed up, but still had 118 seconds to execute. The reason why we tried going with a Java implementation is because Java already has a big integer and parallel thread library built in. But when we went into implementing and trying to convert the code over using those libraries, we ran into a lot of issues and then decided to try a C++ implementation. So let's go ahead and talk about those implementations. Okay, so before I continue on, let's go ahead and just show the idea of what we're trying to do with our parallel. If you see our alphabet, we have 4 elements in the alphabet. If you look at our example DFA, we have 2 elements in the alphabet, meaning that we have 2 transitions between each state. In our example that we're using for our test case, this DFA should have 4 transitions between each state. And if we were able to have 4 cores and have them run in parallel, we could do 1 transition with 1 core and do all 4 transitions in parallel at the same time and hopefully see a speed up. Now, when we look at our actual implementation times, we have a sequential run of 13 seconds. Oops. A sequential time of 13 seconds, and we have a parallel time of 12 seconds. But honestly, after running these multiple times, we would have cases where sometimes the sequential would be faster than the parallel, and we contribute this to the workload of blue at the time of running. Then we also played around with an O3 flag that was used for compiling optimizations. If you look at our sequential, which is the same code as we have up here, it ends up being about 10 seconds quicker. So we went from 13 seconds to just under 3 seconds. And our parallel implementation goes from 12 seconds to just over 3 seconds. So we have a huge speed up, about 10 seconds for both of them. And again, to show you the difference is that all we have is a difference of an O3 flag for these two, but the files are the same for both of these. Now, if we look at our parallel implementation, this is exactly what we were talking about earlier with our states, is that we have 4 threads and we're trying to optimize it for 1 thread for every letter in the alphabet and use that as a transition. Then our threads can use the critical information, which is basically all the updates to the DFA table states, so that we can try and get the answer and not stomp over answers because of race conditions. So with all this implementation, we weren't able to get any kind of speed up that was reliable or significant. But with our O3 flag on the compiler, we got a significant speed up. So we made a graph of our times for Python, Java, and C++, and we really see the computing time based off of really just the languages, where Python, being an interpreted language, takes more time. Java, also being an interpreted language, takes still just as, not as much time as Python, but almost as much. Whereas C++, being so close to the metal, takes very little time in comparison. And what we would have liked to continue to do is, just because of our open MPI, which was what library we're using for C++, there is MPI that allows for more optimizations, but it's a little bit more controlling. We would have liked to see if we could have implemented that and got a better speed up, but weren't able to finish it. Anyways, that was our findings, and I hope you enjoyed our presentation.